Hello and welcome to the last of the lectures in this week 8 of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this week, we have been discussing the interpolativity of fuzzy inference mechanisms. Predominantly in the last 4 lectures, we have discussed the interpolativity of an FRI scheme, a fuzzy relational inference scheme. We have seen that to specify a fuzzy relational inference scheme, we need to specify the coverings, the fuzzy covers over the input and output space, the rules, the way they are formed, where the antecedents AI and the consequence BI are actually picked up from these fuzzy covers, the operation used to relate the antecedent to the consequent to obtain the rules, the relations from the rules, and finally the composition itself. And what we have seen is, if you want to discuss the interpolativity of an FRI, then practically every degree of freedom imposes some conditions, or we need to impose some conditions on all of these different parameters. For instance, when we looked at the composition, then we had to look into the solvability of fuzzy relational equations using those compositions, and we have seen in the last lecture how they directly impinge upon the interpolativity. Not only that, we have also seen the underlying coverings, they should become a partition, and at least on the input domain we need a Ruspini partition to ensure interpolativity. Of course, when we look at the operations involved themselves, then we see the role played by residuated lattices. In this lecture, we will look at interpolativity of similarity based reasoning schemes, and here we will see that we would want some interesting or desirable properties on the matching functions that we employ in the similarity based reasoning schemes. A quick recap of the mechanism underlying a similarity based reasoning scheme. So we are given a CISO rule base, X is AI, then Y is BI. Given an input A dash, we use a matching function to obtain a similarity value, which typically lies between 0 and in the 0-1 interval. These are some examples that we have seen earlier too. Using the similarity value, we modify the consequent of each of the rules, and for this we use a modification function J, which we have anyway seen as can be thought of as just a binary fuzzy logic operation. So these are some modification functions we have seen earlier, and once we obtain the modified consequence from each of the rules, that is we get BI dashes, then what we do is we use an aggregation function G to aggregate all of them into an overall output B dash. Now once again we have seen that this G could be a binary fuzzy logic operation, just that it needs to be associative. Of course, if you want to defuzzify the overall output, we use a defuzzifier, and if the initial input, if it were a real value or a real vector, we appropriately fuzzify it to obtain an input fuzzy set A dash. Let's look at interpolativity itself. We have seen that we are given a set of if-then rules, CISO rules. We have discussed in the classical case what is interpolativity, and we took cue from there. However, there is also an alternate view. We said that fuzzy inference system tries to capture the system function. However, we could also look at the system function itself as a fuzzy mapping, in which case the antecedents and consequence of a rule of rules can be thought of as actually coming from this system function, which gives rise to the partition AI, the antecedents there. And hence, when we are trying to approximate it using our fuzzy inference mechanism, now you can think of it as a psi tilde, which is a function from f of x to f of y, and we will insist that this psi tilde is as close to phi tilde as possible, and as we have seen, one measure of correctness to ensure this is that it is interpolative at these antecedent points. So this is the same as what we have seen earlier, but now it could also be seen from a different view as the system function itself being a fuzzy mapping. Well, we know what a fuzzy covering is. A collection of fuzzy sets on the space says that the union of its supports is actually equal to the space or contains that space. A Ruspini partition is one such that every point, if you consider the membership value of a point to all the fuzzy sets considered in the partition, the sum of the membership values should add up to 1. Now, we want to discuss the interpolativity of an SBR scheme. Let's look at some desirable properties that we would need on the matching function so that we can talk about the interpolativity of the underlying SBR scheme. When do you say a matching function is consistent? Note that matching function essentially takes two fuzzy sets from a particular domain and maps it to the 0-1 interval. We say it is consistent with respect to the underlying space of fuzzy sets if, given any A, M of AA is actually 1. That means if you match a fuzzy set to itself, then it should take the maximum value, which is that of 1. Now, let's look at this particular example, which is the Zardes matching function. Now, if you take any A from f of x, doesn't matter f of x what it is. If A is also normal, then mz of AA is nothing but max x element of x, minimum of A of x, A of x. We know that since A is normal, there will exist a point x0 at which A of x0 is 1. Now, at that point, we could again once again write it as max x0 equal to x0, min of ax, ax, union min of a x0, ax0. We know that at these 2 points it is 1, minimum of these two is 1, so the maximum taken over this entire thing will actually come out to be 1. So clearly, if we consider f of x to be the set of all normal fuzzy sets on x, then the Zardes function is in fact consistent with respect to f of x. So now we need to only consider normal fuzzy sets. Now consider the second matching function ms. ms of a dash is infimum over x, element of x. I is an implication. We have a dash of x, comma, a of x. Once again, let's only consider normal fuzzy sets. However, in this case, even if you consider normal fuzzy sets, if you were to split as infimum x not equal to x naught, I of a dash of x, comma, a of x, min I of a dash of x naught, this would actually be a itself. What we see is this quantity is 1, 1. Since I is an implication, this will turn out to be 1. But what happens here? We do not know what this value will be. If this value goes down below 1, then the infimum would be less than 1. So that means this matching function will not be consistent with respect to the space of normal fuzzy sets that we define on X. To ensure that, what we need is that I has IP, that is I of alpha comma alpha is in fact equal to 1. Now this should happen for every alpha. Now if you insist on this, immediately you will see we don't even need to consider fuzzy sets which are normal, because no matter what value you put here, the same value you will have to put here, and for every x, a of x is alpha, I of alpha alpha is 1, and the infimum for all of them will be 1. So the second matching function that we have, if we employ an implication which also has the identity principle, the identity property, then in fact this is consistent with any space of fuzzy sets. We can also define another property of a matching function called the consistency of a matching function with respect to a fuzzy cover over X. So let's assume that we have a collection of fuzzy sets P which form a fuzzy cover of X, and let's pick some A dash from the set of fuzzy sets. This A dash need not come from P. We say M is consistent with respect to this fuzzy covering if the following property is satisfied. That means when you match this A dash with respect to all of these A case, then the summation of the similarity values should be less than or equal to 1. This is more or less like the Ruspini partition, of course with subadditivity. In Ruspini partition we insist that it should be equal to 1. For example, if we consider A dash to be singleton, then at the point where it is, and insist on equality here, essentially this becomes the Ruspini partition. Are there examples of matching functions which are consistent with respect to a fuzzy covering on X? Well, consider X to be this interval, which is a bounded interval, and let's take A and A dash coming from set of fuzzy sets defined on this X. If we consider this function as the matching function, all we are doing is taking the intersection of A dash and A and taking its area and dividing by the area of A. Clearly, if A dash is A, then MA of AA is 1, so that means it is consistent over this f of X. If we consider a fuzzy covering of this type, it can be easily shown, not without much difficulty, that in fact this matching function is consistent with respect to this fuzzy covering. Note that in this case the space X is actually the interval A1 B5. So this is a matching function which is both consistent on f of X and also consistent with respect to such partitions on X. Now let's come to discussing the interpolativity of similarity based reasoning. Note that the general form of a fuzzy inference scheme, we specify the input and output domains, the rule base, A's are the antecedents and Bj's are the consequence, and the inference operators itself. When it comes to SBR, we have these many degrees of freedom, where Px and Py are the fuzzy coverings on X and Y respectively. R of AA Bj is the fuzzy if-then rule base. M is any matching function. J is any modification function. G is any aggregation function. And H and G are the fuzzifiers and defuzzifiers if they are required. Now, when we are looking at SBR as a fuzzy mapping, then H and G, the fuzzifier and defuzzifier, they do not play a role. So we need to only consider these 5 factors. If we denote the fuzzy function, that the fuzzy mapping that we derive out of specifying these factors, these parameters in an SBR inference scheme, then the psi tilde can be given like this. Of course, it's a mapping from f of X to f of Y. It can be given like this. We need to specify how an output fuzzy set will look like. Let's call that B dash. The B dash is a fuzzy set, so that means its membership value at every Y needs to be specified. So how does B dash of Y look like? It looks like this. So A dash is a fuzzy set on X. So psi tilde of A dash is the mapping that we get on f of Y. It's the mapping, the fuzzy set on Y. Overall, it looks like this. Given this A dash, we match it with each of the antecedents of the rule. Take this similarity value, use the modification function J to modify this Bi, the corresponding consequent, and then finally aggregate using G. So this is the final form, the formula of the inference that we obtain for a given A dash. Let's begin by looking at some sufficiency conditions to ensure interpolativity in an SBR inference scheme. Let's fix the coverings to be actually specified in terms of A alphas, where alpha runs over some index at I, and Py, again it's a fuzzy cover on Y, with respect where the B betas are given, where beta is running over index chain. The rule base is formed by picking AIs from PX and BIs from these B betas. M, J, and G are the matching, modification, and aggregation function. Let's fix each of these and consider the following SBR mode. Px and Py are the fuzzy coverings on X and Y. We don't insist anything more on it. But we insist that J actually satisfies the following condition. We know that J can be thought of as a binary fuzzy logic operation. So we want that if J does satisfy neutrality property, that means 1 is a left neutral element and 0 is in some sense the inverter. So J of 0, y is 1. This is also called the falsity principle in some logical context. So we've just denoted it by FP. But what we want is J of 0, y is 1. If these two properties are satisfied by J, and if G is a commutative associative operation that also satisfies NP, so that means 1 is both left and right neutral element, and the matching function M is both consistent and also consistent with respect to the fuzzy covering Px that we have here. So it satisfies MCF and also MCP with respect to Px. If we consider such a system, the underlying degrees of freedom are chosen in such a way, then the fuzzy mapping induced by the system, psi tilde, is actually interpolated. That means what? Psi tilde of AI is actually equal to BI. Now, how do we prove this? We want to prove that psi tilde of AI is equal to BI. Now, what is psi tilde of A of any A dash at Y? This is what we wrote as B dash of Y. This is given as G, I is equal to 1 to N. There are N rules. J of M of AI, comma A dash, comma BA. Now note that this is for an arbitrary Y element of Y. This can also be further simplified like this. J is the aggregation operator, J of. Note that this is essentially the similarity value Si, BA of Y. Now, note that M satisfies MCP with respect to P of X. This immediately implies sigma M A, A dash is less than or equal to 1. Now, this quantity essentially is Si. So Si, sigma Si is less than or equal to 1. However, note that M also satisfies MCF, which means M of AI, AI is equal to 1. Let's make use of all these properties. So what we want to see is psi tilde of AI should be equal to BI. Now if we substitute it here, B dash at particular Y is actually equal to GA from I to N, J of Si, B of Y for a particular Y. But note that if you were to take this out, when you went to look at what is J of S0, let's also fix this I to be K. So it is very j of s1 comma b1 of y, so on to sk comma bk of y, so on to j of sn comma bn of y. Now, note here, m of ai is 1 means si is 1. Now we have fixed k, so m of ak sk is 1. If sk is 1, rest of the si's, because m has mcp with respect to p, the rest of the si's will be 0. So essentially what we get here is j of 0 comma b naught y comma so on. Only at sk we get the value 1. So this is 0, this is 0, this is 0. Only here we get 1. So we get j of 1 comma bk of y, so on till j of 0 comma bn of y. Now, note that j of 0 comma y is 1, which means we have g of 1 comma 1 is here, and j of 1 comma y is y, so this is bk of y, and rest of them again, because they are all 0, is 1. Now finally, we know that g is both associative and commutative and also satisfies NP, which is g of 1 comma y is y. We know that this turns out to be in fact bk of y. So now what we took was psi tilde of ak of y is in fact bk of y. So now k was arbitrary, y element of y was arbitrary, k element of 1 to n was also arbitrary, which means we have shown that psi tilde of ai is equal to ba for any I. So note that we have not put any conditions on the partitions themselves. They should only be fuzzy coverings, and on the modification and the aggregation function, we have only asked for them to satisfy in some sense some kind of boundary conditions, and of course we put conditions on M such that it is consistent with respect to the fuzzy covering that we are considering. Now, a similar result, another sufficiency condition can be given if we consider the following model. Px and Py are fuzzy coverings on x and y. J now satisfies NP, that is 1 is a left neutral element, and the following condition, which is 0y is in fact 0 instead of 1. So more like a conjunction function. Earlier it looked more like an implication function. And for G, we consider a commutative associative operation such that G of 0y is y. So essentially 0 becomes the neutral element here. So more like a disjunction function. And of course we insist that M satisfies both MCF, that is consistent, and also consistent with respect to the fuzzy covering Px that we have considered here. We can once again show that the fuzzy mapping that we get out of this SBR inference scheme, psi tilde, is in fact interpolating. Well, let's quickly work this out. The proof follows almost along similar lines. So we are looking at psi tilde ak of a y. Now this is G, I is equal to 1 to n, J, Si, Bi of y. Note that from the properties on M, we immediately see if you take ak, so Si is equal to 0 if I is not equal to k, and Si is equal to 1 if I is equal to k. So now if you use this, then the above becomes J of once again 0 comma b1 of y, so until J of 1 comma bk of y, rest of them will turn out to be J of 0 comma bn of y. Now let's look at the conditions on J. J of 0 comma y is 0. So that means this is G of 0 comma. J of 1 comma bky. 1 is the left neutral element of J. So this gives us bk of y. And rest of them are again 0. Now we know that 0 is the left neutral element of G, which means we get bk of y. So once again, k element of Mn was arbitrary, y element of y was arbitrary, which means for any ak that we take, the output from this function psi tilde is in fact the corresponding consequent bk. Now these are some sufficient conditions where we specified conditions on G and J, largely boundary conditions, and of course we insisted on the M being consistent with respect to the fuzzy covering that we are considering. Note that Px is the one that supplies the antecedents to the rules. Now, are there some necessary and sufficient conditions? Well, one such result is available recently. If we consider the following SBR model, once again Px and Py are fuzzy coverings on xy. J is a residual implication of a left continuous T norm T, so we consider J to be IT. G is min, and there are practically no specific conditions on M. That means we do not insist on MCF or MCP. Instead, that condition is translated in a different way. We can show that if we consider such an SBR model, then it will be interpolative if and only if the following inequality is actually valid. What does this inequality say? Take any two I and j, any pair of elements I and j. If their matching values, m of aj is less than or equal to this quantity on the right hand side, then this system is in fact interpolative. Once again, you will see the role played by residual implication. That means this IT is actually coming from a residuated lattice structure. The moment you pick your operations from a residuated lattice structure, we are able to give much more stringent guarantees than what was available earlier. Of course, this is possible because of the richness of the structure, the myriad properties that a residuated lattice has. In fact, if M is commutative, for example, if you consider the example MS, it is not a commutative matching function. If M is commutative, then the above condition actually looks like this. Now, it's been highlighted in blue because you might remember that it is similar such condition that we have seen was important to obtain interpolativity in an FRA scheme. Of course, this is the by implication obtained from IT. We will have more to say in one of the upcoming lectures about how this equation is related to the interpolativity equation for an FRA. We will see that in one special lecture dealing with FRIs and SBRs, theta and fatty. But for now, the take-home message is, if you are choosing your operations from a residuated lattice structure, then often we are able to guarantee stronger results. Well, a quick recap. In this lecture, we discussed interpolativity of SBR mechanisms. Once again, we saw the role of residuated lattices. If we were discussing sufficiency conditions, yes, sufficiency conditions only, they are not necessary. But then we had leeway on the kind of operation that we could use for J and G. On matching function, we wanted it to be consistent with respect to the input fuzzy cover from which we pick the antecedent. However, if J were to come from a residuated lattice structure, if you consider it to be an implication IT, then we were able to give stronger results. We were able to give a condition which was both necessary and sufficient. In the next week of lectures, we will discuss continuity of fuzzy inference systems. Many of these results that we have discussed in this lecture are relatively recent, new, and can be found in this work. We will meet in the next week to discuss continuity of fuzzy inference systems. Glad you could join us for this lecture and hope to see you soon again in the next week of lectures. Thank you again.